Subscribe to Boring Science for sleep for new videos every day. Now, let us begin. The electromagnetic spectrum, which is to say the entire range of electromagnetic radiation that is known to propagate through the vacuum of space and through various material media, constitutes one of the most fundamental and pervasive phenomena in the whole of physical science. Electromagnetic radiation, it must be stated at the outset, is a form of energy that is transmitted through space in the form of oscillating electric and magnetic fields, and these fields are oriented perpendicular to one another and perpendicular to the direction in which the radiation is propagating. This basic description, which was first formulated in a rigorous mathematical framework in the 19th century, has remained essentially unchanged in its fundamental character, though the details of the theory have been refined considerably in the intervening decades and centuries. The story of how electromagnetic radiation came to be understood in its present form is a story that stretches back many centuries, though the most significant advances were made in the period between approximately 1820 and 1905. It was during this period that the relationships between electricity, magnetism, and light were gradually uncovered, and the theoretical framework that unifies these seemingly disparate phenomena was constructed. The earliest investigations into the nature of electricity and magnetism were conducted independently, as the two phenomena were not initially recognized as being related to one another. Static electricity had been observed since antiquity, with the ancient Greeks having noted that amber, when rubbed with fur, could attract small objects such as bits of straw and feathers. The word electricity itself is derived from the Greek word elektron, meaning amber, and this etymological connection serves as a reminder of the long history of human engagement with electrical phenomena. Magnetism, similarly, had been known since ancient times with lodestones, which are naturally magnetized pieces of the mineral magnetite, having been observed to attract iron and to align themselves in a north-south direction when suspended freely. The Chinese are generally credited with having developed the first magnetic compasses, which were in use by approximately the 11th century, and these instruments were subsequently adopted by European navigators and explorers. However, the underlying nature of magnetism remained poorly understood for many centuries, and it was not until the early 19th century that the connection between electricity and magnetism began to be appreciated. The pivotal discovery that linked electricity and magnetism was made by the Danish physicist Hans Christian Ørsted in 1820, when he observed that a compass needle was deflected when placed near a wire carrying an electric current. This observation, which was made during a lecture demonstration, indicated that electric currents produce magnetic fields, and it prompted a flurry of experimental and theoretical activity. André-Marie Ampère, a French physicist and mathematician, quickly followed up on Ørsted's discovery by conducting a series of experiments that established the mathematical relationship between electric currents and the magnetic fields they produce. Ampère demonstrated that two parallel wires carrying electric currents exert forces on one another, with parallel currents attracting and antiparallel currents repelling, and he formulated a mathematical law, now known as Ampere's law, that describes the relationship between an electric current and the magnetic field it generates. In the years following Ørsted's discovery, Michael Faraday, an English scientist who is widely regarded as one of the greatest experimentalists in the history of physics, made a series of discoveries that further elucidated the relationship between electricity and magnetism. In 1831, Faraday discovered electromagnetic induction, the phenomenon whereby a changing magnetic field produces an electric field, and hence an electric current in a conductor. This discovery, which was made independently by the American physicist Joseph Henry at approximately the same time, established that the relationship between electricity and magnetism is reciprocal. Not only do electric currents produce magnetic fields, but changing magnetic fields produce electric fields. Faraday's law of electromagnetic induction, as it came to be known, is one of the foundational principles of electromagnetism, and it underlies the operation of electric generators, transformers, and many other devices that are essential to modern technology. Faraday, it should be noted, did not express his discoveries in mathematical form, as he was largely self-taught and lacked formal training in mathematics. Instead, he developed a qualitative picture of electromagnetic phenomena based on the concept of lines of force, which he imagined as filling the space around magnets and current-carrying conductors. This conceptual framework, while lacking mathematical rigor, proved to be remarkably fruitful and provided the foundation upon which the mathematical theory of electromagnetism was subsequently constructed. The task of translating Faraday's physical insights into a rigorous mathematical theory was accomplished by the Scottish physicist James Clerk Maxwell, whose contributions to the understanding of electromagnetism are regarded as among the most significant achievements in the history of science. Between 1861 and 1865, Maxwell developed a set of equations, now known as Maxwell's equations, that describe the behavior of electric and magnetic fields and their interactions with matter. These equations, of which there are 4 in their modern formulation, encapsulate the entirety of classical electromagnetism in a compact and elegant mathematical form. The first of Maxwell's equations is Gauss's law for electricity, which states that the electric flux through any closed surface is proportional to the total electric charge enclosed within that surface. In mathematical terms, this is expressed as the divergence of the electric field being equal to the charge density divided by the permittivity of free space, which has a value of approximately 8.854 times 10 to the negative 12 farads per meter. This equation describes how electric charges serve as sources and sinks of electric field lines, with positive charges acting as sources from which field lines emanate and negative charges acting as sinks into which field lines terminate. The second of Maxwell's equations is Gauss's law for magnetism, which states that the magnetic flux through any closed surface is always 0. This equation reflects the empirical observation that magnetic monopoles, that is, isolated north or south magnetic poles, have never been found to exist in nature. Every magnet that has ever been observed possesses both a north pole and a south pole, and if a magnet is broken in half, each piece is found to be a complete magnet with its own north and south poles. The divergence of the magnetic field is therefore always zero, and magnetic field lines always form closed loops, never beginning or ending at any point. The third of Maxwell's equations is Faraday's law of electromagnetic induction, which states that a time-varying magnetic field produces an electric field. More precisely, the curl of the electric field is equal to the negative rate of change of the magnetic field with respect to time. This equation provides the mathematical description of the phenomenon that Faraday discovered experimentally in 1831, and it explains how changing magnetic fields can drive electric currents in conductors. The fourth of Maxwell's equations is the Ampere-Maxwell law, which is an extension of Ampere's original law to include the effects of changing electric fields. Ampere's original law stated that the curl of the magnetic field is proportional to the electric current density, but Maxwell recognized that this law, as originally formulated, was incomplete. He introduced an additional term, known as the displacement current, which accounts for the magnetic field produced by a changing electric field. The inclusion of this term was Maxwell's most original and significant contribution, and it was this modification that made the equations self-consistent and led to the prediction of electromagnetic waves. When Maxwell examined his completed set of equations, he discovered that they predicted the existence of waves consisting of oscillating electric and magnetic fields that could propagate through empty space at a speed determined by the permittivity and permeability of free space. The permeability of free space, denoted by the Greek letter mu with a subscript 0, has a value of approximately 1.257 times 10 to the negative 6 henries per meter. And when this value is combined with the permittivity of free space in the appropriate manner, the resulting speed is found to be approximately 299,792,458 meters per second. Maxwell immediately recognized that this value was essentially identical to the speed of light, which had been measured by various experimental methods and was known to be approximately 3 times 10 to the 8 meters per second. This coincidence, Maxwell concluded, could not be mere happenstance, and he proposed that light itself is an electromagnetic wave. This identification of light as an electromagnetic wave was one of the great unifications in the history of physics, as it brought together the previously separate domains of optics and electromagnetism under a single theoretical framework. The speed of light in a vacuum, which is conventionally denoted by the letter c, was subsequently defined to be exactly 299,792,458 meters per second in 1983, when the International System of Units was revised to define the meter in terms of the speed of light. The experimental confirmation of Maxwell's prediction came in 1887, when the German physicist Heinrich Hertz successfully generated and detected electromagnetic waves in his laboratory. Hertz used an oscillating electric circuit to produce the waves and a loop of wire with a small gap to detect them, observing sparks in the gap when the detector was placed at various positions relative to the transmitter. Hertz's experiments demonstrated that these electromagnetic waves exhibited the characteristic properties of waves, including reflection, refraction, and interference, and that they traveled at the speed of light, just as Maxwell had predicted. It is worth noting that Hertz himself did not foresee any practical applications for his discovery, reportedly stating that it was of no use whatsoever. A remark that seems remarkable in retrospect, given the enormous role that electromagnetic waves have come to play in modern communications and technology. The relationship between the wavelength and frequency of an electromagnetic wave is given by the fundamental equation C equals lambda times F, where c is the speed of light, lambda is the wavelength, and f is the frequency. This equation states that the product of the wavelength and the frequency of any electromagnetic wave in a vacuum is always equal to the speed of light. As the wavelength increases, the frequency decreases proportionally, and vice versa. Wavelength is measured in units of length, typically meters or appropriate submultiples thereof, such as nanometers for visible light or kilometers for certain radio waves. Frequency is measured in hertz, where 1 hertz is defined as 1 cycle per second, and multiples such as kilohertz, megahertz, and gigahertz are commonly used for higher frequencies. The wave-particle duality of electromagnetic radiation is one of the most profound and, it must be admitted, conceptually challenging aspects of modern physics. While Maxwell's equations describe electromagnetic radiation as a continuous wave phenomenon, experiments conducted in the late 19th and early 20th centuries revealed that electromagnetic radiation also exhibits particle-like behavior in certain contexts. The photoelectric effect, which was first observed by Heinrich Hertz in 1887 and subsequently studied in detail by Philipp Lenard and others, provided some of the earliest evidence for the particle nature of light. In the photoelectric effect, light incident on a metal surface causes electrons to be ejected from the surface, but the energy of the ejected electrons depends on the frequency of the light rather than its intensity, a result that is difficult to explain on the basis of a purely wave theory. In 1905, Albert Einstein published a paper in which he proposed that light consists of discrete packets of energy, which he called light quanta and which are now known as photons. Einstein's proposal was based on Max Planck's earlier work on blackbody radiation, in which Planck had introduced the concept of energy quantization in 1900. According to Einstein's theory, the energy of a single photon is given by the equation E equals h times f, where E is the energy, h is Planck's constant, and f is the frequency of the radiation. Planck's constant has a value of approximately 6.626 times 10 to the negative 34 joule-seconds, and it is one of the fundamental constants of nature. The energy of a photon is thus directly proportional to its frequency and inversely proportional to its wavelength. High-frequency electromagnetic radiation, such as gamma rays and X-rays, consists of photons with very high energies, while low-frequency radiation, such as radio waves, consists of photons with very low energies. A single photon of visible light, for example, has an energy of approximately 1.8 to 3.1 electron volts, depending on its wavelength and corresponding color, where an electron volt is a unit of energy equal to approximately 1.602 times 10 to the negative 19 joules. A photon of gamma radiation, by contrast, can have an energy of millions or even billions of electron volts, while a photon of radio frequency radiation may have an energy of only 10 to the negative 7 electron volts or less. The development of quantum mechanics in the 1920s and 1930s provided a more complete theoretical framework for understanding the wave-particle duality of electromagnetic radiation and matter. The Copenhagen interpretation of quantum mechanics, which was developed by Niels Bohr, Werner Heisenberg, and others, holds that the wave and particle descriptions of electromagnetic radiation are complementary aspects of a single underlying reality, and that the particular aspect that is manifested depends on the type of measurement or observation that is being performed. In experiments that are designed to detect wave-like properties, such as interference and diffraction experiments, electromagnetic radiation behaves as a wave. In experiments that are designed to detect particle-like properties, such as the photoelectric effect and Compton scattering, electromagnetic radiation behaves as a stream of particles. The Compton effect, which was discovered by Arthur Compton in 1923, and for which he was awarded the Nobel Prize in Physics in 1927, provided further compelling evidence for the particle nature of electromagnetic radiation. Compton observed that when X-rays are scattered by electrons, the scattered X-rays have a longer wavelength than the incident X-rays, and the change in wavelength depends on the angle of scattering. This result is precisely what would be expected if the X-rays consist of particles, that is, photons, that undergo elastic collisions with the electrons, transferring some of their momentum and energy in the process. The Compton wavelength of the electron, which appears in the formula describing this effect, has a value of approximately 2.426 times 10 to the negative 12 meters. The historical development of the understanding of electromagnetic radiation continued throughout the 20th century, with numerous refinements and extensions of the basic theory. Quantum electrodynamics, which was developed in the late 1940s by Richard Feynman, Julian Schwinger, and Shinichiro Tominaga, provided a quantum field theory description of the interaction between electromagnetic radiation and matter that is in extraordinarily precise agreement with experimental measurements. The magnetic moment of the electron, for example, has been measured to agree with the theoretical prediction of quantum electrodynamics to better than 1 part in 10 to the 12th power, making it one of the most precisely tested predictions in all of science. The polarization of electromagnetic radiation is another fundamental property that deserves mention in any comprehensive treatment of the subject. Electromagnetic waves are transverse waves, meaning that the oscillations of the electric and magnetic fields occur in directions perpendicular to the direction of propagation. The polarization of an electromagnetic wave refers to the direction of oscillation of the electric field vector. In a linearly polarized wave, the electric field oscillates in a single plane, while in a circularly polarized wave, the tip of the electric field vector traces out a circle in the plane perpendicular to the direction of propagation, completing one full rotation for each wavelength of travel. Elliptical polarization, in which the tip of the electric field vector traces out an ellipse, is the most general case, with linear and circular polarization being special limiting cases. Unpolarized radiation, such as the light emitted by the sun or by an incandescent lamp, consists of a superposition of waves with random polarization directions, and such radiation can be partially or fully polarized by various processes, including reflection, scattering, and transmission through certain materials. Polaroid filters, which were developed by Edwin Land in the 1930s, are perhaps the most familiar example of polarizing devices and are widely used in sunglasses and photography. The concept of the electromagnetic spectrum as a continuous range of wavelengths and frequencies is so fundamental to modern physics that it is easy to forget how recently this understanding was achieved. As late as the mid-19th century, the various forms of electromagnetic radiation that had been discovered, including visible light, infrared radiation, and ultraviolet radiation, were not recognized as manifestations of a single underlying phenomenon. It was Maxwell's theoretical prediction and Hertz's experimental confirmation of electromagnetic waves that provided the conceptual framework for understanding the electromagnetic spectrum as a unified whole. The subsequent discovery of X-rays by Röntgen in 1895 and of gamma rays by Villard in 1900 extended the known spectrum to much shorter wavelengths and higher frequencies, and the development of radio technology in the early 20th century demonstrated that the spectrum also extended to much longer wavelengths than had previously been known. The Doppler effect, which is the change in the observed frequency of a wave due to relative motion between the source and the observer, applies to electromagnetic radiation just as it does to sound waves, though the detailed mathematical description differs because electromagnetic waves propagate at the speed of light, which is the same in all inertial reference frames according to the theory of special relativity. When a source of electromagnetic radiation is moving toward an observer, the observed frequency is higher than the emitted frequency, and the radiation is said to be blue-shifted. When the source is moving away from the observer, the observed frequency is lower, and the radiation is said to be redshifted. The Doppler effect for electromagnetic radiation has numerous important applications, including the measurement of the velocities of stars and galaxies by observing the shifts in their spectral lines, the measurement of blood flow velocities in medical ultrasound, and the determination of the speeds of vehicles by radar speed guns. The cosmological redshift of distant galaxies, which was first observed by Edwin Hubble in 1929, and which demonstrated that the universe is expanding, is related to the Doppler effect, but is more properly understood as a consequence of the expansion of space itself rather than of the motion of the galaxies through space. It is, perhaps, worth pausing to consider the sheer breadth of the electromagnetic spectrum, which spans an enormous range of wavelengths and frequencies. At the longest wavelength end of the spectrum are radio waves, which can have wavelengths of many kilometers, while at the shortest wavelength end are gamma rays, with wavelengths smaller than the diameter of an atomic nucleus. The ratio of the longest to the shortest wavelengths in the electromagnetic spectrum is on the order of 10 to the 16th power or more, a range that is difficult to comprehend in everyday terms. If the electromagnetic spectrum were represented as a piano keyboard, with each octave corresponding to a doubling of frequency, the keyboard would need to have approximately 50 to 60 octaves, compared to the roughly 7 octaves of a standard piano. Visible light, which is the only portion of the electromagnetic spectrum that is directly detectable by the human eye, occupies less than a single octave of this vast range, corresponding to wavelengths between approximately 380 and 700 nanometers. The electromagnetic spectrum is conventionally divided into several regions or bands, each of which is characterized by a particular range of wavelengths and frequencies, and by the physical mechanisms by which radiation in that band is typically generated and detected. These regions, in order of increasing frequency and decreasing wavelength, are radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. The boundaries between these regions are not sharp or precisely defined, and there is considerable overlap in some cases, but the classification scheme is nonetheless useful for organizing the vast range of electromagnetic phenomena into manageable categories. Each of these regions will be discussed in considerable detail in the sections that follow, with particular attention to the specific wavelength and frequency ranges, the physical characteristics, and the practical applications associated with each band. The propagation of electromagnetic radiation through various media is another topic that merits some discussion at this introductory stage. In a vacuum, all electromagnetic radiation travels at the speed of light, regardless of its wavelength or frequency. However, when electromagnetic radiation enters a material medium, its speed is generally reduced, and the extent of the reduction depends on the properties of the medium and on the frequency of the radiation. The ratio of the speed of light in a vacuum to the speed of light in a particular medium is known as the refractive index of that medium, and it is typically denoted by the letter N. For most transparent materials, the refractive index is greater than 1, indicating that the speed of light in the material is less than the speed of light in a vacuum. The refractive index of glass, for example, is typically in the range of 1.5 to 1.9, depending on the type of glass and the wavelength of the light, while the refractive index of water is approximately 1.33 for visible light. The variation of the refractive index with wavelength, a phenomenon known as dispersion, is responsible for the separation of white light into its constituent colors when it passes through a prism, a phenomenon that was famously investigated by Isaac Newton in 1666. The absorption of electromagnetic radiation by matter is governed by the quantum mechanical properties of the atoms and molecules that constitute the material. When a photon of electromagnetic radiation is absorbed by an atom or molecule, its energy is transferred to the atom or molecule, typically causing a transition from a lower energy state to a higher energy state. The specific wavelengths or frequencies at which absorption occurs depend on the energy level structure of the absorbing species, and this gives rise to characteristic absorption spectra that can be used to identify the chemical composition of materials. Spectroscopy, the study of the absorption and emission of electromagnetic radiation by matter, has been one of the most powerful tools in the physical sciences since its development in the 19th century, and it has found applications in fields ranging from chemistry and physics to astronomy and environmental science. The electromagnetic spectrum, as has been noted, is conventionally divided into several distinct regions, and it is to a detailed examination of each of these regions that we now turn our attention. The divisions of the electromagnetic spectrum are, in order of increasing frequency and decreasing wavelength, radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. It should be emphasized once again that the boundaries between these regions are somewhat arbitrary and are defined primarily by convention and by the practical considerations associated with the generation, detection, and application of radiation in each band. There is no fundamental physical discontinuity at the boundaries. The electromagnetic spectrum is, in reality, a continuous distribution of wavelengths and frequencies. Radio waves occupy the lowest frequency and longest wavelength portion of the electromagnetic spectrum. They are defined as electromagnetic radiation with wavelengths ranging from approximately 1 millimeter to 100 kilometers, corresponding to frequencies ranging from approximately 3 kHz to 300 GHz. However, it should be noted that some classification schemes define radio waves as extending to even longer wavelengths and lower frequencies, and the upper frequency boundary of the radio wave region overlaps with the microwave region. The International Telecommunication Union, which is the specialized agency of the United Nations responsible for information and communication technologies, has established a detailed classification of the radio frequency spectrum into bands, each of which is designated by a number and a name. The extremely low frequency band, abbreviated ELF, encompasses frequencies from 3 Hz to 30 Hz, corresponding to wavelengths from 100,000 kilometers to 10,000 kilometers. Radiation at these frequencies has wavelengths comparable to the diameter of the Earth itself, and it is used primarily for communication with submarines, as these extremely long wavelengths are capable of penetrating seawater to considerable depths. The super low frequency band, abbreviated SLF, covers frequencies from 30 Hz to 300 Hz, with wavelengths from 10,000 kilometers to 1,000 kilometers, and is similarly used for submarine communication. The ultra-low frequency band, abbreviated ULF, spans from 300 Hz to 3 kHz, with wavelengths from 1,000 kilometers to 100 kilometers, and is used for communication in mines and for certain geophysical research applications. The Very Low Frequency Band, abbreviated VLF, covers the range from 3 kHz to 30 kHz, with wavelengths from 100 kilometers to 10 kilometers. VLF signals are capable of propagating over very long distances by reflecting between the surface of the Earth and the ionosphere, and they are used for long-range navigation and for time signal distribution. The low-frequency band, abbreviated LF, spans from 30 kHz to 300 kHz, with wavelengths from 10 kilometers to 1 kilometer, and is used for long-range radio broadcasting, particularly in Europe, and for navigation aids such as the LORAN system. The medium frequency band, abbreviated MF, covers from 300 kHz to 3 MHz, with wavelengths from 1 kilometer to 100 meters, and is the band used for AM radio broadcasting, which typically occupies the frequency range from 530 kHz to 1,710 kHz. The high-frequency band, abbreviated HF, spans from 3 MHz to 30 MHz, with wavelengths from 100 meters to 10 meters. This band is used for shortwave radio broadcasting, amateur radio communication, and over-the-horizon radar, and it is notable for its ability to propagate over very long distances by reflection from the ionosphere, a property that has made it invaluable for international communication since the early 20th century. The Very High Frequency Band, abbreviated VHF, covers from 30 MHz to 300 MHz, with wavelengths from 10 meters to 1 meter, and is used for FM radio broadcasting, which typically occupies the frequency range from 88 MHz to 108 MHz, as well as for television broadcasting and air traffic control communications. The ultra-high frequency band, abbreviated UHF, spans from 300 MHz to 3 GHz, with wavelengths from 1 meter to 100 millimeters, and is used for television broadcasting, mobile telephone communications, wireless networking, and satellite communications. Radio waves are generated by a variety of mechanisms, the most common of which involves the acceleration of electric charges in an antenna. When an alternating current is applied to an antenna, the electrons in the antenna are caused to oscillate back and forth, and this oscillation produces electromagnetic waves that radiate outward from the antenna. The frequency of the emitted radiation is determined by the frequency of the alternating current, and the pattern of radiation depends on the geometry of the antenna. Natural sources of radio waves include lightning, which produces broadband radio emissions across a wide range of frequencies, and certain astronomical objects, such as pulsars, quasars, and the remnants of supernovae. Microwaves are electromagnetic radiation with wavelengths ranging from approximately 1 millimeter to 1 meter, corresponding to frequencies from approximately 300 MHz to 300 GHz. It will be noted that this definition overlaps considerably with the upper portion of the radio wave spectrum, And indeed, the distinction between microwaves and radio waves is somewhat arbitrary. Microwaves are often further subdivided into bands designated by letters, a convention that originated during World War II for reasons of military secrecy. The L band covers frequencies from 1 to 2 GHz, the S band from 2 to 4 GHz, the C band from 4 to 8 GHz, the X band from 8 to 12 GHz, the Q band from 12 to 18 GHz, the K band from 18 to 27 GHz, the Ka band from 27 to 40 GHz, and various additional bands extend to higher frequencies. Microwaves are of considerable practical importance for a variety of applications. Microwave ovens, which operate at a frequency of approximately 2.45 GHz, heat food by causing water molecules to rotate in response to the oscillating electric field of the microwave radiation, a process known as dielectric heating. The frequency of 2.45 GHz was chosen not because it corresponds to a resonance frequency of water, as is sometimes erroneously stated, but rather because it falls within an industrial, scientific, and medical band that is allocated for non-communication purposes, and because it provides a suitable depth of penetration into food. Microwave communication systems, including satellite communication links and terrestrial point-to-point links, operate at various frequencies within the microwave band and are capable of carrying large amounts of data due to the high bandwidth available at these frequencies. Radar, which is an acronym for radio detection and ranging, is another major application of microwave technology. Radar systems operate by emitting pulses of microwave radiation and detecting the reflections from distant objects, allowing the range, direction, and velocity of the objects to be determined. The development of radar technology during the 1930s and 1940s played a crucial role in World War II, and radar systems continue to be used extensively for air traffic control, weather monitoring, military surveillance, and many other purposes. The wavelength of the microwave radiation used in a radar system determines the angular resolution of the system and the size of the objects that can be detected, with shorter wavelengths providing higher resolution, but being more susceptible to attenuation by rain and atmospheric moisture. Infrared radiation occupies the portion of the electromagnetic spectrum between microwaves and visible light, with wavelengths ranging from approximately 700 nanometers to 1 millimeter, corresponding to frequencies from approximately 300 gigahertz to 430 terahertz. The infrared region was discovered in 1800 by the astronomer Sir William Herschel, who was conducting experiments to measure the temperatures associated with different colors of light that had been separated by a prism. Herschel placed a thermometer just beyond the red end of the visible spectrum and observed that the temperature rose, indicating the presence of invisible radiation with a wavelength longer than that of red light. This discovery was one of the first demonstrations that the electromagnetic spectrum extends beyond the range of visible light. The infrared region is conventionally subdivided into 3 subbands, though the exact boundaries vary somewhat among different classification schemes. Near-infrared radiation, sometimes abbreviated NIR, encompasses wavelengths from approximately 700 nanometers to 1,400 nanometers, or in some classifications, to 2,500 nanometers. This region is closest in wavelength to visible light and shares some of its characteristics, including the ability to be focused by glass lenses and detected by certain types of photographic film and semiconductor detectors. Near-infrared radiation is widely used in telecommunications, particularly in fiber optic communication systems, which typically operate at wavelengths of 850 nanometers, 1,310 nanometers, or 1,550 nanometers. The wavelength of 1,550 nanometers is particularly important because it corresponds to a minimum in the attenuation of silica-based optical fibers, allowing signals to be transmitted over distances of many kilometers without amplification. Mid-infrared radiation, sometimes abbreviated MIR, covers wavelengths from approximately 1,400 nanometers or 2,500 nanometers to approximately 8,000 nanometers or, in some classifications, to about 25,000 nanometers or 25 micrometers. This region is of particular importance for chemical analysis and spectroscopy, as many molecules have characteristic vibrational absorption bands in the mid-infrared. The fundamental vibrational frequencies of chemical bonds, such as the carbon-hydrogen bond, the oxygen-hydrogen bond, and the carbon-oxygen bond, correspond to mid-infrared wavelengths and the pattern of absorption in this region, which is often referred to as the molecular fingerprint, can be used to identify and quantify chemical species. Fourier transform infrared spectroscopy, abbreviated FTIR, is a widely used analytical technique that exploits this property for chemical identification and analysis. Far-infrared radiation, sometimes abbreviated FIR, encompasses wavelengths from approximately 25 micrometers to 1 millimeter, placing it adjacent to the microwave region. Far-infrared radiation is associated primarily with thermal emission from objects at relatively low temperatures. All objects with a temperature above absolute zero emit electromagnetic radiation, and for objects at temperatures typically encountered on Earth, the peak of this thermal emission falls in the infrared region. The human body, for example, with a surface temperature of approximately 310 Kelvin or 37 degrees Celsius, emits thermal radiation with a peak wavelength of approximately 9.3 micrometers, which falls in the mid-infrared range. Far-infrared radiation is used in certain types of astronomical observations, as many astronomical objects emit strongly at far-infrared wavelengths, and it is also used in some industrial heating and drying applications. Visible light, which is the portion of the electromagnetic spectrum that is detectable by the human eye, occupies a remarkably narrow band of wavelengths extending from approximately 380 nanometers at the violet end to approximately 700 nanometers at the red end. This range corresponds to frequencies from approximately 430 terahertz for red light to approximately 790 terahertz for violet light. The fact that the human visual system has evolved to be sensitive to this particular range of wavelengths is generally attributed to the fact that the sun, which is the primary natural source of illumination on Earth, emits the greatest proportion of its radiation in and near this wavelength range, and that the Earth's atmosphere is largely transparent to radiation at these wavelengths. Within the visible spectrum, the different wavelengths of light are perceived by the human visual system as different colors. The conventional ordering of the colors of the visible spectrum, from longest wavelength to shortest, is red, orange, yellow, green, blue, indigo, and violet, a sequence that is sometimes remembered by the mnemonic Roy G. Biv. Red light has wavelengths in the range of approximately 620 to 700 nanometers, with a frequency of approximately 430 to 480 terahertz. Orange light occupies the wavelength range from approximately 590 to 620 nanometers, corresponding to frequencies of approximately 480 to 510 terahertz. Yellow light has wavelengths from approximately 570 to 590 nanometers, with frequencies from approximately 510 to 530 terahertz. Green light spans the wavelength range from approximately 495 to 570 nanometers, corresponding to frequencies of approximately 530 to 606 terahertz. Blue light has wavelengths from approximately 450 to 495 nanometers, with frequencies of approximately 606 to 668 terahertz. Indigo, which is sometimes omitted from simplified descriptions of the visible spectrum, occupies a narrow range from approximately 420 to 450 nanometers. Violet light, the shortest wavelength visible radiation, has wavelengths from approximately 380 to 420 nanometers, corresponding to frequencies of approximately 714 to 790 terahertz. The perception of color is, it must be acknowledged, a complex physiological and psychological phenomenon that depends not only on the wavelength of the incident light, but also on the properties of the human visual system and the processing performed by the brain. The human retina contains two types of photoreceptor cells: rods, which are responsible for vision in dim light and are not sensitive to color, and cones, which are responsible for color vision and function primarily in bright light. There are three types of cone cells, designated as S cones, M cones, and L cones, which are maximally sensitive to short wavelength, medium wavelength, and long wavelength light, respectively. The S cones have a peak sensitivity at approximately 420 nanometers, the M cones at approximately 534 nanometers, and the L cones at approximately 564 nanometers. The perception of any particular color is determined by the relative stimulation of these three types of cones, and the brain combines the signals from the three cone types to produce the subjective experience of color. Ultraviolet radiation, abbreviated UV, occupies the portion of the electromagnetic spectrum immediately beyond the violet end of the visible spectrum. with wavelengths ranging from approximately 10 nanometers to 380 nanometers, corresponding to frequencies from approximately 790 terahertz to 30 petahertz. Ultraviolet radiation was discovered in 1801 by the German physicist Johann Wilhelm Ritter, who observed that silver chloride, which was known to darken upon exposure to light, darkened even more rapidly when exposed to radiation beyond the violet end of the visible spectrum. This discovery, which came just 1 year after Herschel's discovery of infrared radiation, further demonstrated the existence of electromagnetic radiation beyond the limits of human vision. The ultraviolet region is conventionally subdivided into several subbands. Ultraviolet A radiation, abbreviated UVA, encompasses wavelengths from 315 nanometers to 380 nanometers and is sometimes referred to as long-wave ultraviolet or black light. UVA radiation constitutes approximately 95% of the ultraviolet radiation from the sun that reaches the Earth's surface, as it is not significantly absorbed by the ozone layer. UVA radiation penetrates deep into the skin, reaching the dermis, and is the primary cause of skin aging and wrinkling. It also contributes to the development of skin cancer, though to a lesser extent than UV radiation. Ultraviolet B radiation, abbreviated UV, covers wavelengths from 280 nanometers to 315 nanometers and is sometimes referred to as medium-wave ultraviolet. UV radiation is partially absorbed by the ozone layer, with the extent of absorption increasing at shorter wavelengths. The UV radiation that reaches the Earth's surface is the primary cause of sunburn and is a significant risk factor for the development of skin cancer, including both basal cell carcinoma and squamous cell carcinoma. UV radiation is also responsible for stimulating the production of vitamin D in the skin, a process that involves the photolysis of 7-dehydrocholesterol to form pre-vitamin D3, which subsequently undergoes thermal isomerization to form vitamin D3. Ultraviolet C radiation, abbreviated UVC, encompasses wavelengths from 100 nanometers to 280 nanometers and is sometimes referred to as shortwave ultraviolet. UVC radiation is almost entirely absorbed by the ozone layer and the atmosphere, and virtually none of it reaches the Earth's surface under normal conditions. UVC radiation is highly effective at destroying microorganisms, including bacteria, viruses, and mold spores, as it is strongly absorbed by nucleic acids and causes damage to the DNA and RNA of these organisms. This germicidal property is exploited in various applications, including water purification, air disinfection, and the sterilization of medical equipment and surfaces. Artificial sources of UVC radiation, such as low-pressure mercury vapor lamps, which emit strongly at a wavelength of 253.7 nanometers, are widely used for these purposes. The extreme ultraviolet, abbreviated EUV, covers wavelengths from approximately 10 nanometers to 121 nanometers and is sometimes classified as a separate region of the spectrum rather than as a subband of the ultraviolet. UV radiation is strongly absorbed by all materials, including air, and can only propagate in a vacuum. It is of considerable importance in certain advanced technological applications, most notably in extreme ultraviolet lithography, a technique that is used to manufacture semiconductor devices with feature sizes of 7 nanometers and below. UV lithography systems operate at a wavelength of 13.5 nanometers and use reflective optics coated with multi-layer thin films of molybdenum and silicon to focus the radiation onto the semiconductor wafer. The vacuum ultraviolet, abbreviated VUV, encompasses wavelengths from approximately 10 nanometers to 200 nanometers and derives its name from the fact that radiation at these wavelengths is strongly absorbed by air and can therefore only be studied in a vacuum or in certain specially chosen gases. The Lyman series of hydrogen, which consists of spectral lines corresponding to transitions from higher energy levels to the ground state of the hydrogen atom, falls entirely within the vacuum ultraviolet region. The Lyman alpha line, which corresponds to the transition from the first excited state to the ground state, has a wavelength of 121.567 nanometers and is the strongest spectral line in the hydrogen emission spectrum. It is also worth noting that the boundaries between the ultraviolet subbands, while widely used in dermatology, photobiology, and atmospheric science, are not universally agreed upon, and different organizations and scientific disciplines may use slightly different wavelength ranges. The International Commission on Illumination, known by its French acronym CIE, defines the UVA band as 315 to 400 nanometers, UV as 280 to 315 nanometers, and UVC as 100 to 280 nanometers, while some dermatological references use 320 nanometers rather than 315 nanometers as the boundary between UVA and UV. These minor discrepancies in the definitions serve as a reminder that the subdivisions of the electromagnetic spectrum are conventions of human classification rather than features inherent in the physics of electromagnetic radiation itself. The sun protection factor, abbreviated SPF, that is printed on sunscreen products is a measure of the degree of protection provided against UV radiation specifically. An SPF of 30, for example, indicates that the sunscreen allows approximately 1/30 of the UV radiation to reach the skin, or equivalently, that a person wearing the sunscreen can be exposed to approximately 30 times as much UV radiation before experiencing sunburn as the same person without sunscreen. It should be noted that the SPF rating does not directly measure protection against UVA radiation, which is assessed by separate systems such as the PA rating system used in Japan and several other Asian countries, or the STAR rating system used in the United Kingdom. The detailed examination of each of these subdivisions of the electromagnetic spectrum reveals the remarkable richness and diversity of electromagnetic phenomena. From the extremely long wavelengths of ELF radio waves, which have wavelengths comparable to the circumference of the Earth, to the extremely short wavelengths of the extreme ultraviolet, which are comparable to the sizes of large molecules. The portion of the spectrum considered thus far spans a range of approximately 13 orders of magnitude in wavelength. And yet, as will be discussed in the following sections, the spectrum extends still further in both directions, with X-rays and gamma rays occupying the regions of even shorter wavelengths and higher frequencies. X-rays, which occupy the portion of the electromagnetic spectrum with wavelengths ranging from approximately 0.01 nanometers to 10 nanometers, corresponding to frequencies from approximately 30 pHz to 30 exahertz, were discovered on November 8, 1895, by the German physicist Wilhelm Conrad Röntgen while he was conducting experiments with cathode rays in his laboratory at the University of Würzburg. Röntgen observed that a fluorescent screen placed near his cathode ray tube glowed even when the tube was enclosed in a thick cardboard shield, indicating that some form of previously unknown radiation was being emitted by the tube and was capable of penetrating the cardboard. He subsequently found that this radiation could also penetrate many other materials, including wood, paper, and thin sheets of metal, and that it caused photographic plates to darken. Unable to determine the nature of this radiation, Röntgen designated it with a mathematical symbol for an unknown quantity, calling it X-radiation or X-rays, a name that has persisted in English and many other languages. Though in German-speaking countries the radiation is sometimes referred to as Röntgenstrahlung or Röntgen radiation. Röntgen's discovery was met with enormous public interest and scientific excitement. Within weeks of the announcement of his findings, which were published in late December 1895, physicians and scientists around the world were experimenting with X-rays, and the first medical X-ray images were produced. Röntgen himself produced one of the earliest and most famous X-ray images, a radiograph of his wife Anna Bertha's hand, in which the bones and her wedding ring are clearly visible. The diagnostic potential of X-rays was immediately recognized, and within a few years, X-ray imaging had become an established medical technique. Röntgen was awarded the first Nobel Prize in Physics in 1901 for his discovery, and he donated the prize money to his university. X-rays are produced by two principal mechanisms. The first is the deceleration of fast-moving charged particles, typically electrons, when they interact with the electromagnetic field of an atomic nucleus or are otherwise subjected to a rapid change in velocity. This process produces Bremsstrahlung radiation, a German term meaning breaking radiation, and the resulting X-ray spectrum is continuous, extending from zero frequency up to a maximum frequency determined by the kinetic energy of the incident particles. In a typical X-ray tube, electrons are accelerated through a potential difference of approximately 20,000 to 150,000 volts and then directed at a metal target, typically made of tungsten, molybdenum, or copper. When the electrons strike the target, they are rapidly decelerated, and a portion of their kinetic energy is converted into X-ray radiation. The efficiency of X-ray production by this mechanism is quite low, typically on the order of 1% or less for conventional X-ray tubes, with the remainder of the energy being converted into heat. The second mechanism of X-ray production is the emission of characteristic X-rays, which occurs when an electron in an inner shell of an atom is removed by the impact of a high-energy electron or photon, and an electron from a higher energy shell transitions to fill the vacancy. The energy of the emitted X-ray photon is equal to the difference in energy between the two electron shells, and since these energies are characteristic of the particular element, the resulting X-ray spectrum consists of discrete lines at specific energies and wavelengths. The characteristic X-ray lines of an element are designated by letters that indicate the shell from which the electron was ejected and the shell from which the replacement electron originated. For example, the K-alpha line corresponds to a transition from the L shell to the K shell, and the K-beta line corresponds to a transition from the M shell to the K shell. The application of X-rays in medical imaging has been one of the most significant practical outcomes of Röntgen's discovery. Conventional radiography, which produces a two-dimensional projection image of the internal structures of the body, relies on the differential absorption of X-rays by different types of tissue. Bone, which is dense and contains calcium, absorbs X-rays much more strongly than soft tissue, and this differential absorption produces the contrast that makes bones visible in a radiograph. Computed tomography, abbreviated CT, which was developed in the 1970s by Sir Godfrey Hounsfield and Alan Cormack, both of whom were awarded the Nobel Prize in Physiology or Medicine in 1979, uses X-rays to produce detailed cross-sectional images of the body. A CT scanner rotates an X-ray source and detector around the patient, collecting absorption data from many different angles, and a computer algorithm is then used to reconstruct a three-dimensional image of the internal structures. X-ray crystallography is another application of X-rays that has had an enormous impact on science. When X-rays are directed at a crystalline material, they are diffracted by the regularly spaced atoms in the crystal lattice, producing a characteristic pattern of spots on a detector. By analyzing this diffraction pattern, it is possible to determine the arrangement of atoms within the crystal with very high precision. X-ray crystallography was developed in the early 20th century, principally by William Henry Bragg and his son William Lawrence Bragg, who shared the Nobel Prize in Physics in 1915 for their work. Bragg's law, which describes the conditions under which constructive interference occurs for X-rays diffracted by a crystal, states that n times lambda equals 2d times the sine of theta, where n is an integer, lambda is the wavelength of the X-rays. D is the spacing between crystal planes, and theta is the angle of incidence. X-ray crystallography has been used to determine the structures of an enormous number of materials, including metals, minerals, semiconductors, and biological molecules. Perhaps the most famous application of X-ray crystallography was the determination of the structure of DNA by James Watson and Francis Crick in 1953, which relied in part on X-ray diffraction data obtained by Rosalind Franklin and Maurice Wilkins. Gamma rays occupy the highest frequency and shortest wavelength region of the electromagnetic spectrum, with wavelengths shorter than approximately 0.01 nanometers and frequencies greater than approximately 30 exahertz. The boundary between X-rays and gamma rays is not defined by wavelength or frequency alone, but rather by the mechanism of production. Radiation produced by nuclear transitions or nuclear reactions is classified as gamma radiation, while radiation produced by electronic transitions or the deceleration of charged particles is classified as X radiation. This means that there is a region of overlap in wavelength between X-rays and gamma rays, and a photon with a given wavelength may be classified as either an X-ray or a gamma ray depending on how it was produced. Gamma rays were first identified in 1900 by the French physicist Paul Villard, who observed that the radiation emitted by radium consisted of 3 distinct components, which were subsequently designated as alpha, beta, and gamma radiation by Ernest Rutherford. Alpha radiation was found to consist of helium nuclei, beta radiation of electrons or positrons, and gamma radiation of high-energy electromagnetic waves. Gamma rays are emitted by atomic nuclei when they undergo transitions from higher energy states to lower energy states, a process that is analogous to the emission of visible light or X-rays by electrons undergoing transitions between electronic energy levels, but occurring at much higher energies due to the much stronger nuclear forces involved. The energy of gamma-ray photons is typically measured in units of kiloelectron volts or megaelectron volts. Gamma rays emitted by radioactive isotopes used in medical imaging, such as technetium-99m, have energies of approximately 140 kiloelectron volts, while gamma rays produced in certain nuclear reactions and astrophysical processes can have energies of many megaelectron volts or even gigaelectron volts. The most energetic gamma rays ever detected by astronomical observatories have energies on the order of several tera-electron volts, or 10 to the 12th electron volts, and these are produced by extreme astrophysical phenomena such as gamma-ray bursts, active galactic nuclei, and the interactions of ultra-high-energy cosmic rays with the cosmic microwave background radiation. The relationship between the wavelength of electromagnetic radiation and its penetrating power is a general principle that applies across the entire electromagnetic spectrum. As a broad generalization, shorter wavelength radiation tends to be more penetrating than longer wavelength radiation. Though the detailed relationship between wavelength and penetration depends on the specific material and the wavelength range under consideration. Radio waves, which have the longest wavelengths, are generally stopped by thick walls of metal or concrete, though they can penetrate wood, plastic, and many other non-metallic materials. Visible light is stopped by opaque materials, but passes freely through transparent ones. X-rays can penetrate soft tissue, but are absorbed by bone and dense metals. Gamma rays are the most penetrating form of electromagnetic radiation and can pass through considerable thicknesses of material, requiring dense shielding materials such as lead or depleted uranium to attenuate them. The attenuation of electromagnetic radiation as it passes through matter is described mathematically by the Beer-Lambert law, which states that the intensity of the radiation decreases exponentially with the thickness of the material through which it passes. The rate of attenuation is characterized by the linear attenuation coefficient, which depends on the properties of the material and on the energy of the radiation. For X-rays and gamma rays, the attenuation coefficient generally decreases with increasing photon energy, meaning that higher energy photons are more penetrating. However, the relationship is not monotonic, as there are sharp increases in the attenuation coefficient at energies corresponding to the absorption edges of the elements in the material. The interaction of electromagnetic radiation with the Earth's atmosphere is of considerable importance for many practical and scientific applications. The atmosphere is largely opaque to electromagnetic radiation at most wavelengths, with two principal transmission windows through which radiation can pass relatively freely. The first and most familiar of these windows is the optical window, which encompasses the visible spectrum and extends into the near-infrared and near-ultraviolet regions, from approximately 300 nanometers to approximately 1,100 nanometers. The second major window is the radio window, which extends from approximately 1 centimeter to approximately 10 meters in wavelength. Between these two windows, the atmosphere is largely opaque due to absorption by various atmospheric constituents, primarily water vapor, carbon dioxide, and ozone. Ozone, which is a molecule consisting of 3 oxygen atoms and is concentrated in the stratosphere at altitudes between approximately 15 and 35 kilometers, is primarily responsible for absorbing ultraviolet radiation with wavelengths shorter than approximately 320 nanometers. This absorption is of critical importance for life on Earth, as UVC and most UV radiation is harmful to biological organisms and would cause widespread damage to DNA and other biomolecules if it were to reach the surface unattenuated. The discovery in the 1980s that human-produced chlorofluorocarbons were depleting the ozone layer and allowing increased amounts of ultraviolet radiation to reach the surface led to the Montreal Protocol, an international agreement signed in 1987 to phase out the production and use of ozone-depleting substances. Water vapor is the primary absorber of infrared radiation in the atmosphere, with strong absorption bands at numerous wavelengths throughout the infrared region. Carbon dioxide also absorbs infrared radiation at specific wavelengths, most notably at approximately 4.3 micrometers and approximately 15 micrometers. These absorption properties are of central importance to the greenhouse effect, whereby certain atmospheric gases absorb infrared radiation emitted by the Earth's surface and re-radiate it in all directions, including back toward the surface, thereby warming the surface to a temperature higher than it would otherwise be. The greenhouse effect is a natural phenomenon that has maintained the Earth's surface temperature at habitable levels throughout most of its history. But the enhanced greenhouse effect resulting from increased atmospheric concentrations of carbon dioxide and other greenhouse gases due to human activities is the primary driver of contemporary climate change. The concept of blackbody radiation is fundamental to the understanding of the electromagnetic spectrum and its relationship to temperature. A blackbody is an idealized object that absorbs all electromagnetic radiation incident upon it and emits radiation at all wavelengths in a manner that depends only on its temperature. The spectrum of radiation emitted by a blackbody is described by Planck's law, which was formulated by the German physicist Max Planck in 1900. Planck's law gives the spectral radiance of a blackbody as a function of wavelength and temperature, and it states that the spectral radiance is proportional to the inverse of the wavelength raised to the fifth power, multiplied by the inverse of the exponential of hc divided by lambda times k times t minus 1, where h is Planck's constant, c is the speed of light, lambda is the wavelength, k is Boltzmann's constant, which has a value of approximately 1.381 times 10 to the negative 23 joules per Kelvin, and T is the absolute temperature in kelvins. Planck's law predicts that the spectrum of blackbody radiation has a characteristic shape, rising from zero at very short wavelengths to a peak at a wavelength that depends on the temperature, and then declining at longer wavelengths. The wavelength at which the spectrum peaks is given by Wien's displacement law, which states that the peak wavelength is inversely proportional to the temperature. Specifically, the peak wavelength in meters is equal to Wien's displacement constant, which has a value of approximately 2.898 times 10 to the negative 3 meter kelvins, divided by the temperature in kelvins. For the Sun, which has a surface temperature of approximately 5,778 kelvins, Wien's displacement law predicts a peak wavelength of approximately 501 nanometers, which falls in the green portion of the visible spectrum. For the human body, with a surface temperature of approximately 310 kelvins, the peak wavelength is approximately 9.35 micrometers, which falls in the mid-infrared region. For the cosmic microwave background radiation, which has a temperature of approximately 2.725 kelvins, the peak wavelength is approximately 1.063 millimeters, which falls in the microwave region. The total power radiated by a blackbody per unit surface area is given by the Stefan-Boltzmann law, which states that the total radiant excitance is proportional to the fourth power of the absolute temperature. The constant of proportionality is the Stefan-Boltzmann constant, denoted by the Greek letter sigma, which has a value of approximately 5.670 times 10 to the negative 8 watts per square meter per Kelvin to the fourth power. The Stefan-Boltzmann law was first deduced empirically by Joseph Stefan in 1879 from experimental measurements, and it was subsequently derived theoretically by Ludwig Boltzmann in 1884 using thermodynamic arguments. According to this law, the Sun, with its surface temperature of approximately 5,778 kelvins, radiates approximately 6.33 times 10 to the 7th watts per square meter, or approximately 63.3 megawatts per square meter from its surface. The derivation of Planck's law marked a pivotal moment in the history of physics, as it required Planck to introduce the revolutionary hypothesis that electromagnetic energy is emitted and absorbed in discrete quantities, or quanta. rather than continuously. This hypothesis was necessitated by the failure of classical physics to account for the observed spectrum of blackbody radiation. Classical physics, specifically the Rayleigh-Jeans law, predicted that the spectral radiance of a blackbody should increase without limit as the wavelength decreases, a result that was obviously at odds with observation, and that was dubbed the ultraviolet catastrophe by Paul Arifest in 1911. The Rayleigh-Jeans law is a correct prediction of classical physics and agrees well with experimental observations at long wavelengths, but it diverges dramatically from observation at short wavelengths, predicting infinite total radiated power, which is physically impossible. Planck resolved the ultraviolet catastrophe by postulating that the energy of the oscillators responsible for emitting and absorbing electromagnetic radiation is quantized, meaning that it can only take on values that are integer multiples of hf, where h is Planck's constant and f is the frequency. This quantization hypothesis, which Planck initially regarded as a mathematical trick rather than a statement about physical reality, effectively suppresses the contribution of high-frequency oscillators to the total radiated energy. Because at high frequencies, the energy quantum hf is large, and the probability of an oscillator having sufficient energy to emit at that frequency decreases exponentially with frequency. Planck's law thus smoothly interpolates between the Rayleigh-Jeans law at long wavelengths and the Wien approximation at short wavelengths, and it provides an exact description of the observed blackbody spectrum at all wavelengths. The introduction of energy quantization by Planck in 1900 is generally regarded as the birth of quantum mechanics, though the full implications of Planck's hypothesis were not appreciated until several years later. It was Einstein's 1905 paper on the photoelectric effect, in which he proposed that light itself is quantized into photons, that first extended the quantization concept from the emission and absorption of radiation to the radiation itself. The subsequent development of quantum mechanics in the 1920s by Werner Heisenberg, Erwin Schrödinger, Max Born, Paul Dirac, and others provided a comprehensive theoretical framework that explained not only blackbody radiation and the photoelectric effect, but also a vast range of other phenomena, including atomic spectra, chemical bonding, and the properties of solids. The quantum theory of electromagnetic radiation, which reached its most complete form in the development of quantum electrodynamics in the late 1940s, remains one of the most successful and precisely tested theories in all of physics. It is worth noting that the Planck distribution function can also be expressed in terms of frequency rather than wavelength, and the two forms, while describing the same physical phenomenon, have their peak values at different points. The peak of the frequency form of the Planck distribution occurs at a frequency given by a modified form of Wien's displacement law, where the peak frequency in Hertz is approximately equal to 5.879 times 10 to the 10th power multiplied by the temperature in kelvins. This apparent discrepancy between the wavelength and frequency forms of the peak is not a contradiction, but rather a consequence of the nonlinear relationship between wavelength and frequency and the different ways in which the spectral energy density is distributed when expressed per unit wavelength versus per unit frequency. The emissivity of real materials, which describes how closely they approximate a blackbody, varies between 0 and 1 and generally depends on the wavelength, the temperature, and the surface properties of the material. Materials with high emissivity, such as soot, dark paint, and certain ceramics, emit radiation at a rate close to that of a blackbody at the same temperature, while materials with low emissivity, such as polished metals, emit radiation at a much lower rate. The concept of emissivity is of considerable practical importance in thermal engineering, as it determines the rate at which objects lose heat by radiation, and it is also important in remote sensing and thermal imaging, where the emissivity of the surface must be known in order to accurately determine its temperature from the measured thermal radiation. Kirchhoff's law of thermal radiation, formulated by Gustav Kirchhoff in 1860, states that for a body in thermal equilibrium, the emissivity at a given wavelength is equal to the absorptivity at that wavelength, meaning that good absorbers of radiation are also good emitters, and poor absorbers are poor emitters. The relationship between blackbody radiation and the electromagnetic spectrum has profound implications for astronomy and astrophysics. Stars, to a good approximation, emit radiation as black bodies, and the temperature of a star's surface, or photosphere, can be inferred from the wavelength at which its emission spectrum peaks. Hot stars, with surface temperatures exceeding 10,000 kelvins, emit most of their radiation in the ultraviolet, and they appear blue-white to the human eye. Cool stars, with surface temperatures of 3,000 kelvins or less, emit most of their radiation in the infrared, and they appear red. The Sun, with its intermediate surface temperature of approximately 5,778 kelvins, emits most strongly in the visible range and appears yellow-white. The classification of stars by their spectral characteristics, which is closely related to their surface temperatures, was systematized in the late 19th and early 20th centuries and forms the basis of the Morgan-Keenan spectral classification system, which categorizes stars into spectral types designated O, B, A, F, G, K, and M, in order of decreasing temperature. The practical applications of electromagnetic radiation span the entirety of the electromagnetic spectrum and have transformed virtually every aspect of modern life, from communications and entertainment to medicine, industry, and scientific research. It is to a systematic survey of these applications, organized by region of the spectrum, that this final portion of our discussion is devoted. The applications to be discussed are, of necessity, selective rather than exhaustive, as the full range of uses of electromagnetic radiation is so vast that a comprehensive treatment would require many volumes. Radio broadcasting, which was one of the earliest practical applications of electromagnetic radiation and which remains an important medium of communication to this day, relies on the transmission and reception of radio waves at frequencies in the medium frequency and very high frequency bands. Amplitude modulation broadcasting, commonly known as AM radio, operates at frequencies between 530 kHz and 1710 kHz, and it encodes the audio signal by varying the amplitude of the carrier wave while keeping its frequency constant. Frequency modulation broadcasting, commonly known as FM radio, operates at frequencies between 88 MHz and 108 MHz, and it encodes the audio signal by varying the frequency of the carrier wave while keeping its amplitude constant. FM broadcasting generally provides higher audio quality than AM broadcasting, as it is less susceptible to interference from electrical noise and atmospheric disturbances, but AM broadcasting has the advantage of longer range, particularly at night, when AM signals can propagate over great distances by reflecting from the ionosphere. Television broadcasting, which began in the 1930s and has since become one of the most ubiquitous forms of mass communication, originally used analog signals transmitted at VHF and UHF frequencies. The transition to digital television, which has been completed in most countries, has allowed for more efficient use of the radio spectrum and has enabled the transmission of high-definition video and multiple program channels within the bandwidth previously occupied by a single analog channel. Digital television signals are typically transmitted at UHF frequencies, and the freed VHF frequencies have been reallocated for other uses, including mobile communications and emergency services. Mobile telephone communications, which have grown from a niche technology in the 1980s to a service used by more than 5 billion people worldwide, operate at frequencies in the UHF and microwave bands. The first generation of mobile telephone technology, known as 1G, used analog signals at frequencies around 800 MHz. Subsequent generations have used increasingly sophisticated digital modulation and encoding techniques and have migrated to higher frequencies to access additional bandwidth. The fifth generation of mobile telephone technology, known as 5G, which has been deployed since approximately 2019, operates at frequencies ranging from below 1 GHz to above 24 GHz. With the higher frequency bands, known as millimeter wave bands, offering very high data rates but limited range due to increased atmospheric attenuation and susceptibility to obstruction by buildings and other obstacles. Wireless local area networking, commonly known as Wi-Fi, operates at frequencies of 2.4 GHz and 5 GHz, with newer standards also utilizing the 6 GHz band. The 2.4 GHz band provides longer range but lower data rates, while the 5 GHz and 6 GHz bands offer higher data rates but shorter range. These frequencies fall within the microwave region of the electromagnetic spectrum, and the signals are subject to absorption and scattering by walls, furniture, and other objects within buildings. The data rates achievable by modern Wi-Fi systems, which can exceed several gigabits per second under favorable conditions, are a testament to the extraordinary sophistication of modern digital communication technology. Radar systems, as was mentioned in an earlier section, operate at microwave frequencies and are used for a wide range of purposes, including air traffic control, weather monitoring, military surveillance, and automotive collision avoidance. Weather radar, which operates at frequencies in the S-band, around 2 to 4 GHz, and the C-band, around 4 to 8 GHz, is used to detect precipitation and to measure its intensity, motion, and type. Doppler weather radar, which measures the frequency shift of the reflected signal caused by the motion of the precipitation particles, can determine the velocity of the particles and thus provide information about wind patterns within storms. This information is of critical importance for the detection and tracking of severe weather events such as tornadoes, hurricanes, and thunderstorms. Thermal imaging, which is the detection and visualization of infrared radiation emitted by objects, has found numerous applications in both military and civilian contexts. Military applications include night vision systems, which detect the thermal radiation emitted by people, vehicles, and equipment against the cooler background of the natural environment, and infrared-guided missiles, which home in on the thermal signature of their targets. Civilian applications of thermal imaging include building energy audits, in which thermal cameras are used to identify areas of heat loss in buildings, electrical and mechanical inspection, in which thermal cameras are used to detect overheating components in electrical systems and machinery, medical thermography, in which thermal cameras are used to detect areas of abnormal temperature on the body surface that may indicate disease, and firefighting, in which thermal cameras are used to see through smoke and to locate people and hot spots in burning buildings. Spectroscopy, which is the study of the interaction between electromagnetic radiation and matter, is one of the most versatile and widely used analytical techniques in the physical sciences. Different types of spectroscopy utilize different regions of the electromagnetic spectrum and probe different types of molecular and atomic transitions. Infrared spectroscopy, as was mentioned earlier, probes the vibrational modes of molecules and is widely used for chemical identification and analysis. Ultraviolet visible spectroscopy, abbreviated UV-vis, probes electronic transitions in molecules and is used to measure the concentrations of absorbing species in solution and to study the electronic structure of molecules. Nuclear magnetic resonance spectroscopy, abbreviated NMR, which operates at radio frequencies in the range of approximately 60 to 1000 MHz in the presence of strong magnetic fields, probes the magnetic properties of atomic nuclei and is one of the most powerful tools for determining the structures of organic molecules and proteins. Mass spectrometry, though not strictly a form of electromagnetic spectroscopy, is often used in conjunction with spectroscopic techniques to provide complementary information about the masses and structures of molecules. Medical imaging encompasses a range of techniques that use electromagnetic radiation at various wavelengths to produce images of the internal structures of the body. Conventional radiography and computed tomography, which use X-rays, have already been discussed. Magnetic resonance imaging, abbreviated MRI, uses radio frequency electromagnetic radiation in combination with strong magnetic fields to produce detailed images of soft tissues with excellent contrast. The technique relies on the phenomenon of nuclear magnetic resonance, in which atomic nuclei in a magnetic field absorb and re-emit radio frequency radiation at a frequency that depends on the strength of the magnetic field and the magnetic properties of the nucleus. By applying carefully controlled magnetic field gradients across the body, the spatial distribution of hydrogen nuclei, which are abundant in water and fat, can be mapped, producing high-resolution images of the internal anatomy. MRI has the advantage of not using ionizing radiation and is therefore considered safer than X-ray-based imaging techniques for many applications. Positron emission tomography, abbreviated PET, is a medical imaging technique that detects pairs of gamma-ray photons emitted indirectly by a positron-emitting radioactive tracer substance that has been introduced into the body. When a positron emitted by the tracer encounters an electron in the surrounding tissue, the two particles annihilate one another, producing two gamma-ray photons with energies of 511 keV that travel in approximately opposite directions. By detecting these pairs of photons with a ring of detectors surrounding the patient, the location of the annihilation event, and hence the location of the radioactive tracer, can be determined. PET imaging is widely used in oncology, cardiology, and neurology, and it provides functional information about metabolic processes in the body rather than purely anatomical information. Astronomical observations at different wavelengths of the electromagnetic spectrum have revealed a universe that is far richer and more complex than could ever be appreciated from observations in visible light alone. Radio astronomy, which began in the 1930s with Carl Jansky's detection of radio emission from the Milky Way, has led to the discovery of numerous astronomical phenomena, including pulsars, which are rapidly rotating neutron stars that emit beams of radio radiation, quasars, which are extremely luminous active galactic nuclei powered by supermassive black holes, and the cosmic microwave background radiation, which is the remnant thermal radiation from the early universe. Infrared astronomy has revealed the cool universe of dust clouds, protostars, and planetary disks that are invisible at optical wavelengths. Ultraviolet and X-ray astronomy have probed the hot universe of stellar coronae, supernova remnants, and the accretion disks surrounding black holes and neutron stars. Gamma-ray astronomy has detected the most energetic phenomena in the universe, including gamma-ray bursts, which are the most luminous events known to occur, releasing as much energy in a few seconds as the sun will emit over its entire lifetime. The cosmic microwave background radiation, abbreviated CMB, is one of the most important discoveries in the history of astronomy and cosmology. It was predicted theoretically by Ralph Alpher and Robert Herman in 1948 as a consequence of the Big Bang theory of the origin of the universe. And it was discovered accidentally in 1965 by Arno Penzias and Robert Wilson, who were working with a microwave antenna at Bell Telephone Laboratories in Holmdel, New Jersey. Penzias and Wilson observed a persistent background noise in their antenna that corresponded to a temperature of approximately 3.5 kelvins and that appeared to come from all directions in the sky. They were initially unable to explain this noise, but they soon learned of the theoretical prediction by Alpher and Hermann and the identification of the observed radiation as the cosmic microwave background was made. Penzias and Wilson were awarded the Nobel Prize in Physics in 1978 for their discovery. The cosmic microwave background radiation has a spectrum that is an almost perfect blackbody spectrum, with a temperature that has been measured with extraordinary precision by the COBE, WMEP, and Planck satellite missions. The Planck satellite, which operated from 2009 to 2013, measured the temperature of the CMB to be 2.7255 kelvins, with an uncertainty of only 0.0006 kelvins, making it the most precisely measured blackbody spectrum in nature. The peak wavelength of the CMB, as determined by Wien's displacement law, is approximately 1.063 millimeters, which falls in the microwave region of the spectrum, hence the name cosmic microwave background. The CMB also exhibits tiny temperature fluctuations on the order of 1 part in 100,000 that correspond to slight variations in the density of matter in the early universe, and that served as the seeds from which all subsequent structures in the universe, including galaxies, galaxy clusters, and the large-scale cosmic web, eventually formed through the process of gravitational collapse. Electromagnetic shielding is the practice of enclosing electronic devices or spaces with conductive materials to prevent external electromagnetic fields from interfering with the enclosed equipment, or to prevent electromagnetic emissions from the enclosed equipment from reaching the outside environment. A Faraday cage, named after Michael Faraday, who first demonstrated the principle in 1836, is an enclosure made of conductive material, such as a metal mesh or solid metal sheet, that blocks external static and non-static electric fields. When an external electromagnetic field impinges on a Faraday cage, the free charges in the conductive material redistribute themselves in such a way as to cancel the field inside the cage. The effectiveness of a Faraday cage depends on the conductivity and thickness of the material, the size of any openings in the mesh, and the frequency of the electromagnetic radiation. Higher frequency radiation requires smaller mesh openings for effective shielding. Electromagnetic shielding is used in a wide variety of applications. Electronic devices are often enclosed in metal cases or coated with conductive paint to prevent electromagnetic interference, abbreviated EMI, which can cause malfunctions or degraded performance. Hospitals and medical facilities use electromagnetic shielding to protect sensitive medical equipment, such as MRI machines, from external electromagnetic fields. Secure government and military facilities use electromagnetic shielding to prevent the leakage of information carried by electromagnetic emissions, a concern known as tempest in military terminology. Microwave ovens incorporate electromagnetic shielding in their doors and enclosures to prevent microwave radiation from escaping. and the mesh screen visible in the door of a microwave oven is designed to block radiation at the operating frequency of 2.45 GHz while allowing visible light to pass through. The safety standards for human exposure to electromagnetic radiation vary by frequency and are based on the known biological effects of radiation at different wavelengths and intensities. At the lower frequency end of the spectrum, the primary concern is the heating of body tissues by the absorption of electromagnetic energy, a thermal effect that is quantified by the specific absorption rate, abbreviated SAR, which is measured in watts per kilogram of body tissue. The International Commission on Non-Ionizing Radiation Protection, abbreviated IGNIRP, has established guidelines for exposure to electromagnetic fields at frequencies from 1 Hz to 300 GHz. For the general public, the IGNIRP guidelines limit the SR for exposure to radiofrequency electromagnetic fields to 0.08 watts per kilogram averaged over the whole body, and to 2 watts per kilogram averaged over any 10 grams of tissue in the head and trunk. For workers, the limits are higher at 0.4 watts per kilogram for whole body exposure and 10 watts per kilogram for localized exposure. At the higher frequency end of the spectrum, the primary concern is the ionizing effect of ultraviolet radiation, X-rays, and gamma rays, which have sufficient energy to remove electrons from atoms and molecules and thereby cause damage to biological tissues, including DNA damage that can lead to cancer. Exposure to ionizing radiation is measured in units of sieverts, where 1 sievert is defined as the dose of radiation that has the same biological effect as 1 gray of gamma radiation. The average person is exposed to approximately 2 to 3 millisieverts of ionizing radiation per year from natural background sources, including cosmic rays, radon gas, and naturally occurring radioactive isotopes in the body. The ICRP, the International Commission on Radiological Protection, recommends that occupational exposure to ionizing radiation be limited to 20 millisieverts per year averaged over 5 years, with no single year exceeding 50 millisieverts, and that public exposure be limited to 1 millisievert per year above the natural background. The question of whether exposure to non-ionizing electromagnetic radiation at levels below those that cause significant heating effects can have adverse health consequences has been the subject of considerable public concern and scientific investigation. Numerous epidemiological studies and laboratory experiments have been conducted to investigate possible health effects of exposure to radiofrequency electromagnetic fields, such as those produced by mobile telephones and wireless communication systems, and to extremely low-frequency electromagnetic fields, such as those produced by power lines and electrical appliances. The weight of the scientific evidence, as assessed by major national and international health organizations, including the World Health Organization, does not support the conclusion that exposure to non-ionizing electromagnetic radiation at levels below current safety guidelines causes adverse health effects. However, research in this area continues, and some scientists and public health advocates have called for a precautionary approach to exposure, particularly for children, who may be more vulnerable to potential effects due to their developing nervous systems and their longer expected lifetime of exposure. The electromagnetic spectrum, considered in its entirety, represents one of the most fundamental and unifying concepts in the whole of physical science. From the longest wavelength radio waves, with wavelengths of many kilometers, to the shortest wavelength gamma rays, with wavelengths smaller than the diameter of an atomic nucleus, all electromagnetic radiation is fundamentally the same phenomenon. Oscillating electric and magnetic fields propagating through space at the speed of light. The differences between the various regions of the spectrum are differences of degree rather than kind, reflecting the continuous variation of wavelength and frequency and the corresponding variation in the energy of individual photons. The extraordinary range of practical applications that have been developed for electromagnetic radiation at different wavelengths, from radio broadcasting and telecommunications to medical imaging and astronomical observation, is a testament to the fundamental importance of electromagnetic phenomena in the physical world and to the ingenuity of the scientists and engineers who have harnessed these phenomena for the benefit of humanity. Remote sensing, which is the acquisition of information about an object or phenomenon without making physical contact with it, relies heavily on the detection and analysis of electromagnetic radiation at various wavelengths. Satellite-based remote sensing systems observe the Earth from orbit at wavelengths ranging from the visible through the infrared to the microwave region of the spectrum. Landsat satellites, the first of which was launched in 1972, have provided continuous multispectral imagery of the Earth's surface for more than 5 decades, enabling the monitoring of deforestation, urbanization, agricultural practices, and natural disasters on a global scale. Synthetic aperture radar, abbreviated SR, which operates at microwave frequencies and produces its own illumination rather than relying on sunlight, can image the Earth's surface through clouds and in darkness, making it particularly useful for monitoring regions that are frequently covered by cloud, such as tropical rainforests. The Sentinel, one satellite constellation operated by the European Space Agency, carries C-band SR instruments operating at a frequency of 5.405 GHz, providing imagery with a spatial resolution of approximately 5 meters by 20 meters in its interferometric wide swath mode. The interaction of electromagnetic radiation with the human body extends well beyond the medical imaging applications discussed earlier. Phototherapy, which is the therapeutic use of electromagnetic radiation, has been employed for the treatment of various medical conditions. Ultraviolet phototherapy, particularly with UV radiation at wavelengths around 311 nanometers, known as narrowband UV therapy, is widely used for the treatment of skin conditions such as psoriasis, vitiligo, and eczema. Photodynamic therapy uses visible light in combination with photosensitizing drugs to destroy cancerous and precancerous cells, as the photosensitizer selectively accumulates in abnormal tissue and, when activated by light of the appropriate wavelength, generates reactive oxygen species that kill the targeted cells. Laser surgery, which uses highly focused beams of electromagnetic radiation at various wavelengths, has found applications in ophthalmology, dermatology, dentistry, and numerous other medical specialties. The carbon dioxide laser, which emits infrared radiation at a wavelength of 10,600 nanometers, and the neodymium-doped yttrium aluminum garnet laser, known as the ND-YG laser, which emits at a wavelength of 1,064 nanometers, are among the most commonly used surgical lasers. The study of the electromagnetic spectrum has also been intimately connected with some of the most profound developments in theoretical physics. The unification of electricity, magnetism, and light by Maxwell in the 1860s was one of the great triumphs of 19th century physics and served as a model for subsequent attempts at unification. The resolution of the ultraviolet catastrophe by Planck in 1900 and Einstein's explanation of the photoelectric effect in 1905 led to the development of quantum mechanics, which revolutionized our understanding of the physical world at the atomic and subatomic level. The development of quantum electrodynamics in the late 1940s provided a quantum field theory description of electromagnetic phenomena that is in extraordinarily precise agreement with experiment and that has served as a template for the development of quantum field theories of the other fundamental forces of nature. As the understanding of the electromagnetic spectrum has deepened over the past 2 centuries, so too has the appreciation of the role that electromagnetic radiation plays in the natural world. The sun, which emits electromagnetic radiation across the entire spectrum, is the primary source of energy for virtually all life on Earth, and the interaction of solar radiation with the Earth's atmosphere, oceans, and land surfaces drives the climate system and the water cycle. The electromagnetic radiation emitted by distant stars, galaxies, and other astronomical objects carries information about the physical conditions and chemical compositions of these objects across the vast distances of space. And the study of this radiation has enabled humanity to construct a remarkably detailed picture of the universe and its history. The cosmic microwave background radiation, which fills all of space with a faint glow of microwave radiation at a temperature of 2.7255 kelvins, is a relic of the very earliest epoch of the universe. Dating from a time approximately 380,000 years after the Big Bang, when the universe had cooled sufficiently for electrons and protons to combine to form neutral hydrogen atoms, a process known as recombination. Before recombination, the universe was filled with a hot, dense plasma that was opaque to electromagnetic radiation, and the CMB represents the first light that was able to travel freely through space. The study of the CMB has provided some of the most precise constraints on the fundamental parameters of cosmology, including the age of the universe, which is approximately 13.8 billion years, the geometry of the universe, which is very close to flat, and the composition of the universe, which is approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. In the end, The electromagnetic spectrum is not merely a catalog of different types of radiation arranged by wavelength and frequency. It is rather a window into the fundamental nature of the physical world, revealing the deep connections between electricity, magnetism, light, matter, energy, and the very structure of space and time. The story of how this understanding was achieved through the efforts of countless scientists over more than 2 centuries is one of the great intellectual achievements of our species. And the practical applications that have flowed from this understanding have transformed human civilization in ways that would have been unimaginable to the pioneers who first began to explore the mysterious realm of electromagnetic radiation. And with that, we have reached the end of our rather lengthy and, it must be admitted, rather tedious survey of the electromagnetic spectrum and its subdivisions in physical science.